Proceed only after you complete the review assignment posted on Blackboard that covers chapters 3, 6, 7, and 8. Read chapter 9, and then complete reading assignment 9 on Blackboard. In chapter 8, we constructed intervals of the population mean to get an idea of how large or how small it is. In chapter 9, we hypothesize or guess the value of the population mean, and then test whether it is equal to, greater than, or less than the hypothesized value. Hypothesis testing can be used to determine whether a statement about the value of a population parameter should or should not be rejected. Statistics from sample data are used to reject or not reject hypotheses, even though the estimate of population parameter is rarely exact. When a variable is continuous, the probabilities that the sample mean x bar equals the population mean mu, or the sample standard deviation s equals the population standard deviation sigma are both equal to 0. Despite the fact that sample statistics are not exact, we use them to test whether parameters are equal to, less than, or greater than hypothesized values. If the sample mean is close enough to the hypothesized value of the population mean, mu0, then their difference is essentially 0. This difference is the numerator of z and t test statistics. The z statistic is used if the population standard deviation sigma is known, while a t statistic is used if sigma is unknown. If these statistics are not significantly different from 0, population mean mu is probably equal to its hypothesized value. If the sample standard deviation is close enough to the hypothesized value of the population standard deviation, sigma 0, then their ratio is essentially equal to 1. And so too is the ratio of the sample and population variance. This ratio is called a chi-square test statistic. If this statistic is not significantly different from 1, the population variance is probably equal to its hypothesized value. The null hypothesis, denoted HO, is a tentative assumption about a population parameter. A manufacturer's claim is formed as a null hypothesis. The alternative hypothesis, denoted HA, is the opposite of the null hypothesis. A researcher's hypothesis is formed as an alternative hypothesis. If the sample data contradicts the null hypothesis, then either a research hypothesis stated as the alternative hypothesis is true, or a manufacturer's claim stated as the null hypothesis is false. In general, a hypothesis test about the value of population mean mu must take on one of the following forms: the upper tail test, the lower tail test, or the two-tailed test. Notice that the alternative hypothesis determines the type of test. This is an upper tail test because we're looking at mu being greater than the hypothesized value, mu0. This is a lower tail test because we're looking at the population mean, mu, being less than a hypothesized value. This is a two-tailed test because mu is either less than its hypothesized value or mu is greater than the hypothesized value. The equality part of the hypotheses always appears in the null hypothesis. A major West Coast city provides one of the most comprehensive emergency medical services in the world, operating in a multiple hospital system with approximately 20 mobile medical units. The service goal is to respond to medical emergencies. in 12 minutes or less. The director of medical service wants to formulate a hypothesis test that could use a sample of emergency response times to determine whether or not the service goal of 12 minutes or less is being achieved. This is not a research hypothesis. You are verifying the validity of a claim. Hence, the null hypothesis is population mean, mu, is less than or equal to 12 minutes. If the null hypothesis is population mean mu is less than or equal to 12 minutes, then the emergency service is meeting the response goal of 12 minutes or less. The alternative hypothesis would be population mean mu is greater than 12 minutes, which suggests emergency service is not meeting the response goal of 12 minutes or less. If the alternative is true, follow-up action is necessary. That is, the hospital might want to consider buying a helicopter to improve its average response time, for example. What conclusion is appropriate when the null hypothesis cannot be rejected? For example, we could say, we are not able to conclude the director's claim is wrong. What conclusion is appropriate when the null hypothesis can be rejected? The director's claim can be rejected. Because hypothesis tests are based on sample data, we must allow for the possibility of errors. A type 1 error results when a true null hypothesis is rejected. And the probability of making one is equal to alpha, the level of significance. Hypothesis testing that controls for a type 1 error are called significance tests. To control for type 1 error, simply increase or decrease alpha. Example, suppose George is on trial for murdering Jill. In America, people are presumed innocent. Thus, the null hypothesis is George is not guilty. While the alternative hypothesis is George is guilty. A type 1 error occurs if an innocent George is convicted of murder. The probability of making a type 1 error can be lowered by choosing a smaller alpha. A type 2 error results when a false null hypothesis is accepted, and the probability of making one is equal to beta. It is difficult to control for the probability of making a type 2 error. Statisticians avoid the risk of making a type 2 error by using the phrase, do not reject the null hypothesis instead of accept the null hypothesis. Suppose Mark is on trial for murdering John. In America, people are presumed innocent. Thus, the null hypothesis is Mark is not guilty, while the alternative hypothesis is Mark is guilty. A type 2 error occurs if Mark murdered John but is acquitted of murder. Intuitively, setting the numerator of the following statistic equal to 0, x bar minus mu 0 equal to 0, is equivalent to the null hypothesis of a two-tailed test being true. Mu equals mu 0. The textbook refers to this as just z. We will refer to it as z-stat because most statistics software programs call it that. If x is a random variable with an expected value of mu and variance of sigma squared, then A, sample mean x bar is normally distributed with an expected value of mu and a variance of sigma squared divided by the sample size n. B, z-stat, this equation up here, is normally distributed with an expected value of 0 and a variance of 1, provided that one of the following three is true. X is normally distributed, or X's distribution is not heavily skewed and the sample size is 30 or larger. Or X's distribution is heavily skewed and the sample size is big, meaning it's 50 or larger. P-value is probably associated with Z-stat, which is just the deviation from the hypothesized value of the mean divided by the standard deviation of X bar. The P-value for the lower tail test is the probability of being less than Z-stat. P-value for the upper tail test is the probability of being greater than Z-stat. The p-value measures the support or lack of support provided by the sample for the null hypothesis. The p-value approach to the lower tail test compares the significance, alpha, which is equal to 0.1 here, to the p-value, which is found using Z-stat and the standard normal distribution table. Suppose a sample of data generates Z-stat equal to negative 1.46. The value in row 1.4 and column 0.06 is 0.0721. Since the probability that Z is less than or equal to a Z-stat of a negative 1.46 is 0.0721, the p-value is 0.0721. Since this is a lower tailed test with a significance equal to 0.1, the lower tail of the distribution is shaded in red and labeled 0.10. This tail defines the do not reject the null hypothesis and reject the null hypothesis regions. The blue tail probability is smaller than the red tail probability because Z-stat equal to a negative 1.46 has a p-value equal to 0.0721, which is smaller than 0.10. When the p-value, the blue area, is smaller than the alpha, the red area, we reject the null hypothesis at the 10% level of significance. Notice that Z-stat is in the reject the null hypothesis region.